Welcome to ePachala lecture series and computer science. We are discussing paper Cryptography Network Security. In this module we are going to discuss about exponentiation and logarithmics. The objective of this particular module is to discuss about the exponentiation and logarithmic algorithms, to understand the need for order of group, to know about the purpose of primitive root, and also various examples related to the topic. So, what is exponentiation and logarithmics? How it is related? So, exponentiation is y is equal to a power x. So, in the cryptography, most of the encryption process we use exponentiation. So, if we take a RSA algorithm or LGAML, any algorithm if we take, we always do an exponentiation. That is, if I want to encrypt a text, I will take the text and the power x as the secret and y as the ciphertext. So, doing exponentiation is straight forward, very easy. That means the other word, finding the logarithm of given value, it is very difficult. So, that is what we say as trapdoor function. So, always whenever I go for any encryption process or a decryption process, the user will prefer for going for this exponentiation, but the attacker, by knowing the a and y, if I know a because some part of the text I can and y, then it is very difficult for get back the x value. So, finding this logarithm, if I know a and y without knowing a, it is very difficult for getting me the x value. So, that is the purpose we want to understand about this logarithm. So, logarithm in cryptography, we also we need to know about modular logarithm. So, earlier it is just a definition for exponentiation logarithm in the field of mathematics, but with respect to the field of cryptography, we also need to know about modular logarithm. So, modular logarithm is nothing but y is congruent to x mod n return x or else return failure. So, modular underscore logarithm a y n is given, a is given, y is given, n is given, then we can do this for exhaustive search. If k is the number of bits in x, the k is the number of bits in x, k is the number of bits in x, then from x 1 to n minus 1 we do the exponentiation and we try to get the value of x. So, otherwise it is going to be a failure. Discrete logarithms in mathematics, a discrete logarithm is an integer k exponent solving the equation bk is equal to g, where b and g are element of group. So, when I am taking a integer exponent, that is b power k is equal to g, where b and g are b power k is equal to g, where b and g are element of the group, then we can say it is going to be a discrete logarithm, where I say an integer exponent, k exponent. So, discrete logarithms are the logarithm defined with regards to multiplicative cyclic group. So, we need to know what is cyclic group and also what is multiplicative cyclic group in order to define about the discrete logarithm. So, if I want to know about discrete logarithm, first thing I want to understand about cyclic group, then I want to know what is multiplicative cyclic group, then with respect to I define a logarithm, then I say it is going to be a discrete logarithm. So, if G is a multiplicative cyclic group, that is capital G, and there is a generator small g. If I assume G as a multiplicative cycle group and G small g is a generator of capital G, that means the group multiplicative cycle group where there exists an element G is a generator of capital G, then forms the definition of cycle group. So, we know that every element H in G can be written as G power x for some x. So, that is why it is called generator. So, what is a generator here? The generator must able to generate every element in the cyclic group. So, if I am taking a multiplicative cyclic group and there exists a generator G, then definitely the generator G with respect to some x should able to give a value of H in G. That means every element in G. Then we can say G is a multiplicative cyclic group. So, the discrete logarithm to the base G of H in the group is defined to be x. So, we say base G of H in the group G is defined to be x. Suppose I am taking, for example, if you want to understand this definition, where we can take a group, a multiplicative cycle group, let us assume a group with Z phi with multiplicative operation, that star is a multiplicative operation, and if there is a generator 2, so we say there is a generator 2, then the discrete logarithm of 1 is 4 because 2 power 4 congruent to 1 mod phi, 2 power 4 congruent to 1 mod phi. Now, we map this example with respect to the statement given before. We have a capital G here, capital G is a multiplicative cycle group, that is Z phi of multiplication operation. So, we can say that here this is our multiplicative cycle group and there is a generator, this is capital G and there is a generator smaller g is equal to, then what is the discrete logarithm here? We can able to understand is G, what is G here? 2, the base G of H, what is H? Here is 4, congruent to 1 mod phi. So, 2 power 4 is 16, mod 5 is 15, that is a remainder is 1. So, we can say 1, then the discrete logarithm of 1 is 4, discrete logarithm of 1 is 4 with respect to the cyclic group where the generator is G. So, now I can say this is a multiplicative cyclic group where suppose I want to find the discrete logarithm of 1. How can I find the discrete logarithm of 1 is 2 power 4, the 4 is what we say as the value which is used to get the discrete logarithm of 1. So, 2 power 4 is congruent to 1 mod phi. So, now in the case of your discrete log, fix a prime p, let a and a comma b be non-zero integer mod p, that means you can say a comma b as a non-zero integer. The problem to finding x such that a x is congruent to b mod p is called discrete log problem. So, this is what we say in the case of any cryptographic asymmetric key algorithm. We used to say that the process of encryption is, though it is going to be computationally complex, but it is easier when compared to breaking the algorithm with the knowledge of some information. We call that as a discrete log problem. So, now if I say p is prime, that is fixed here, and there are two non-zero integer, if I say ax congruent to b mod p, then by knowing a or b, it is very difficult to know what is x. Then I call this problem as discrete log problem. So, now I hope you can understand how this is helping in the case of our encryption process, how it is making our encryption processes more secure, because the reason is if I say a prime number, that is a mod p, if I say a and b are non-negative integer, I am multiplying an x as an unknown information to the attacker. If you know a and b are mod p, it should be very difficult for him to get back the value what is x, maybe it is your private key, then this comes under your discrete log problem. Suppose that n is smallest integer such that congruent 1 mod p, that is we say n order of p of a, by assuming that 0 less than or equal to x less than n, we denote x is LA of b, that is logarithmic of b, then and it is called discrete log of b with respect to a. So, we say that x is discrete log of b with respect to a mod p. We can say that it is x is discrete log of b with respect to a mod p. So, here is an example. Let us assume the p is 11, that is your prime number, and a is equal to 2, b is equal to 2. Then what is the x here? X is L2 of 9 is equal to 6. So, before going to understand of this discrete logarithmic problem, we already know that this discrete log generated with the help of our multiplicative cyclic group and a generator of G. So, we need to understand about the cyclic group and generators. So, what is a cyclic group and what is a generator? How we can able to identify a generator? Some group have, we know the group is one of the component of your abstract algebra, where group have interesting property. All the element in the group can be obtained by repeatedly applying the group operation to a particular group element. So, we know what is a group. A group is a set of element where it can able to have the property like commutative, or we can associative, identity, inverse, then we can say all the elements are in that group. So, now if a group has such a property, that means what is the property here? Interesting property, an additional property to some groups only having the such a property, except that we can say all the element in this group can be obtained by repeatedly applying the group operation to a particular group element. So, that is what we need to understand. So, when I say, when I choose one element and do a group operation repeatedly, where it can able to generate all the elements in the group, then I can say if a group has such a property, it is called a cyclic group, and the element in the group which can able to generate all the elements in the group by repeatedly applying the group operation is called generator. So, now we can able to understand what is cyclic group, what is generator. Cyclic group is having some special property that if I choose one element and repeatedly I am applying group operation where I can able to generate all the elements in the group, then I can say it is a cyclic group, and the element which I am used for generating all the element is called generator, all the other elements called generator. A trivial example here is group Zn is the additive group of integer modulo n, that means set of natural number integers. So, here in Zn 1 is always a generator when I say it is an additive group of integer modulo of n. So, I say that n is an integer. When I am choosing one value, that is 1 as a generator, then I should be able to generate all the elements in the particular group. So, when I say 1 is congruent 1 mod n, then I say 1 plus 1, that is going to be provide me 2 mod n. 1 plus 1 plus 1, that means here it is an additive group, that is why we are adding 1 plus 1 plus 1 is equal congruence to 3 mod n. like that I do n mod n is equal. So, we can able to see here all the numbers are belongs to this group Zn, which was generated with the help of a generator 1 by using the property group operation addition. So, now I can say here the Zn is a cyclic group and 1 is our generator, where it can generate all the elements in that particular group. If a group is cyclic, then we know there may exist a multiple generator also. There are certain cases, if I say last case where we are taken 1 as a generator, there are certain groups where we can have more than one generator, one element will be a generator. As we are taking an example, Z5 is a cyclic group, the element 1 is a generator for sure, because we are taken 1, already we know whatever the value of n definitely will able to generate all the element in that. So, n is one generator. Now, we assume that we take the 2 as another one generator, where we can able to repeatedly performing an addition operation. For example, if I take Z5 is an additive operation as the group operation, 2 congruent to mod 5, if I add 2 plus 2, 4 congruent to mod 5, then 2 plus 2 plus 2, 6 is congruent to 6, mod 5 is 1 mod 5, congruent to 1 mod 5. Similarly, I do for 8, 3 mod 5, similarly I do for 10, 12. Again you can be able to see that if I go for example here, you can see 0, 1, 2, 3, 4 till 5 I will get, right. 0, 1, 5 elements, 0, 1, 2, 3, 4. Okay. That is what our elements within this particular cyclic group Z of 5. So, what are the elements here we have? All the groups elements are 0, 1, 2, 3, 4 in Z5 can also be generated by 2. Now, we can say that for example, I go for 2 plus 2 plus 2 plus 2 plus, I am adding another one 2, 12. Again I go for mod operation, 12 mod 5 I will get 2, again it is also a member of this particular group element. Then I say 14 mod, then 4, then 16 mod, then I will say 1, like that. Whenever I do repeatedly the operation of the particular group, the generator must providing all the elements within that particular group. We say that is a cyclic group, and a new generator what we got with respect to our already we know the one is one generator, and also there are some groups there may exist multiple generator. One of the example here is we can say that 2 is also generator of group Z5. So, now we can able to understand that the cyclic group as well as the generator, which is going to play a very important role in the case of your discrete. In addition to that, we also need to know about order of a group. So, we know what is cyclic group, we know what is a generator. Now, what is an order of a group G? For example, I am taking Z21 with multiplicative operation. So, we know very well with the help of your Euler-Taussian function or Euler phi function, the simplest Euler phi function which we have discussed under the Euler's theorem, phi of 21. The first thing I want to find the order of a group. If a group is given as G is equal to Z 21 star comma x, that is multiplicative operation, then phi of 21 with the help of the rules which are given for Euler-Taussian function, we know very well 21 can be factorized as 3 into 27, 3 into 7. So, 3 into 7 we get 21. So, phi of 3 into phi of 7, that means this is a prime number, this is another prime number. So, always we will be factorizing in cryptography with the help of prime numbers. So, phi of 3 into phi of 7, we know the rule for finding the phi of 3, whenever I have a phi of p, I say p minus 1. Whenever I say phi of p, I will say p minus 1. That is the answer for this particular operation. So, phi of 3 is equal to p minus 1. What is p here? P is 3, 3 minus 1 is 2. Similarly, phi of 7, that is p minus 1, that is 7 minus 1 is 6. So, 2 into 6 is equal to 12. So, there are 12 elements in this group. So, we are finding order of a group. We say 12 elements. We say 12 elements are there in this particular group, and we want to find out all the elements of this particular group, and all these are relatively prime with 21. So, if you do 1 comma 21 GCD of 1 comma 21 1, 2 comma 21 GCD of 2 comma 21 1, 4 comma 21 1, the answer is 1, 5 comma 21 the GCD of 5 comma 21 is 1. So, we can understand here the order of the group is 12, and the elements which are there in the particular group are 12, 1, 2, 4, 5. Why we are not choosing 3? We know very well 3 comma 21, GCD of 3 comma 21, it is not equal to 1, right. So, that is why we are not taking the 3. Similarly, 6 we are not taking, 9 we are not taking, because these are multiple of 3, and definitely there is a GCD value other than 1 there will be there, which are not relatively prime elements. The listed numbers are relatively prime numbers with respect to 21. So, now we know how to find order of a group G. Let us take an example. Find order of all the elements in G and a group Z10 into 10. So, we know very well 10, only 4 elements. How we got this? With the help of Euler phi function. How can we write 10? 10 can be write as 2 into 5, phi of 2 into 5, that means p minus 1, that is 2 minus 1 1, then we have 5 minus 1 4, 1 into 4 we have 4 elements. Now, we are going to find out the relatively prime element within that particular 10, that is from 1 to 10, which are relatively prime. 1, 3, 7, 9 are relatively prime. Now, we have to find out the order of each element by trial and error. So, first we are taking 1, we start with 1 power 1 is congruent to 1 mod n, where order of 1 is 1. So, we got here is 1. So, what is the idea here is, I start with the element which are available in the group with 1, next I will go for 1 power 2, 1 power 3, 1 power 4, like that I will be keep on trying in the trial and error way. At one point of time I will get 1 as the answer for any power what is given. So, based on this I will find the order of the element. Here I say that when I having a element to the power which results the congruence of 1, then I say that is the order of an element. For example, order of 1 is 1 because the power is 1. Order of 3 is 4 because we know that 3 power 4 mod 10 is equal to 1, then order of 3 is equal to 4. Similarly, order of 4, 7 power 4 is equal to is congruent to 1 mod 10, then order of 7 is 4. Then 9 square, that is 9 power 2, that is 81, is mod 10, where a remainder is 1, I say order of 9 is equal to 2. So, this is the way. Here the previous thing where we find the order of a group with the help of Euler's totem function, here we find order of an element with a trial and error way to get each and element's order. Now, with the help of this we are going to define the primitive root. What is primitive root? In a group G, Zn star of multiplicative operation, when the order of an element is same as the phi of n, then the element is called primitive root, right. If I take a group, in that group when the order of an element is same as that of phi of n, we say that element is the primitive root of the group. So, if I want to find the primitive root of any group, first thing I want to know order of a group, second thing I want to know order of an element, then what I have to do? I need to verify whether order of an element is equal to order of a group. So, here for example, in this case, if I want to know about or if I want to find the primitive root according to the definition or according to the statement which is given, I want to know order of an element and also order of a group. Here order of a group is 4 and I want to know which are the element. Suppose I am having 1, 3, 7, 9. From this element, which element order is equal to 4, then I can say that element is primitive root of given group. So what is that here? I can say 3 and 7 are primitive element of group Z10 of multiplication operation. So, whereas this element order is not equal to order of the group, then one cannot be a primitive element. Similarly, 9 is also not in the order of 4, then we can't say that is an primitive element. So, primitive element in a group G Z of multiplicative operation where the order of an element is same as that of order of n, then that element is called primitive root of the group. So, for example, here there are no primitive root in G is equal to Z8 multiplicative operation because no element has order of 4. Always when we do a trial and error method, the order of the elements are smaller than 4. So, there are certain groups we do not have the primitive element. So, now take an example. For example, I want to know which are the primitive element. If I take ai congruent to x mod 7 for the group G is equal to Z7 of multiplicative operation, in this group phi of 7 is equal to 6, we know that is 7 is a prime number, directly we can say the order of the group is phi of 7 is equal to 6. Then I take all the elements in that particular group. For example, it is 6 means 1 comma 7 is the GCD of 1 comma 7 is equal to 1, GCD of 2 comma 7 is equal to 1, 3 comma 7. So, all the elements, if I say a group with prime number, then all the elements will be co-prime to that particular element n. So, I get all the values a 1, 2, 3 like that. Then I will go for trial and error. First I will start with 1 power 1 mod 7, then 1 power 2 mod 7, always I will get 1, then x power 1 power 6 mod, that is what it is given here. A power I is congruent to x mod of 7, right. So, then I am taking 2 power 1 is 2 mod 7 and 2 power 2 where I get 4 mod 7, then 2 power 3 I am getting 8, that is 1 here, 8 mod 7. Similarly, I go for A4, again you will get 1 here 1, but exactly which elements are primitive root, because always we say that order of group should be 6 and also the order of element should be 6. So, we have 1 for this element of 3 and 5. So, we can say that the primitive root for this group Z7 is 3 and 5. So, like that we can do for any group, we can able to say what is the possibility of getting the primitive roots. So, discrete logarithm, the idea of discrete logarithm property of G is ZP star multiplicative operation. Its elements include all the elements from 1 to p minus 1, that is what we say, and it is always have primitive roots. That means order of all the elements definitely should match the order of the group, and it is also a cyclic. The element can be created using a generated g power x of x integer from 1 to phi of n, that is p minus 1. The primitive roots can thought as the base of logarithm. So, now I think we understood what is discrete log property with respect to a group. So, we say that all the elements include from p to 1 to p minus 1 and always have a primitive root, then it is a cyclic with a generator and the root primitive root thought as the base for logarithm. Then I can say that particular root having the property of discrete log. So, that function it's very difficult to break. So, here we say that compared with your traditional logarithm and also with the discrete logarithm. So, log a of 1 is equal to 0, log a x into y is we have such a property. With respect to your discrete log generator here g, right, Lg of 1 is equal to 1 mod phi of n, which is your order of the group. Similarly, g we can say the same property with the model. So, here discrete log where we have a modulus in the particular operation. So, discrete log problem has the same complexity as that of your factorization problem what we used in the case of your cryptography. So, we come to the conclusion to say that we learned about the exponentiation and also what is the inverse is a logarithmic algorithm, and also we observed the need for how to satisfy the property of discrete log with respect to your order of the group, and also what is cyclic group, and also how to find the primitive root of an element or the purpose of primitive root with respect to your discrete logarithm, and also what is discrete log problem, how it is helping in the case of your cryptography. Thank you.